Okay, welcome back. So you may have been thinking about this little puzzle. The purpose of the puzzle is not to try and come up with a closed form solution. The purpose is really just to exercise recursion. It's much easier to solve it using recursion than it is to solve the recursion itself and eliminate the recursion altogether. So the purpose is really to see that recursion is fairly straightforward to handle. So the way you think about it is, imagine we've solved it for some number of lines. In this example picture, we have 4 lines. Now suppose we were to add one more line. How many more intersections would we get if we add one more line? Well, the best case is, the best we can do if we add one more line, is we add a line which cuts through each of the lines that are already there. So if there are 4 lines there, the new line, the 5th line, will cut through all 4 of them. If there are 10 lines there, the new line will cut through all 10 of them. So when we want to work out the number of lines, sorry, the number of intersections, for some case of n, when n, let's say n is greater than 1, some non-trivial case, suppose you know what the answer is for the number of intersections for n minus 1. Suppose you know what that is. There it is. How many more lines, how many more intersections will you get by adding one more line to the n minus 1? Well, for each of the n minus 1 lines, you get one more intersection. So you get a total of n minus 1 new intersections by adding one line. You get n minus 1 plus the recursive case. So we've solved the recursive case without having to do anything particularly clever, other than just imagining how we would solve the bigger problem in terms of a slightly smaller problem. And the base case well, there's various base cases. Let's just take the base case of 1. If we have just one line, then we know we have 0 intersections. Or we could generalize this to all the other cases. I don't know what it means to have a negative number of lines, but anyway. Okay? All right. Okay, we're not going to spend ages going on and on about recursion. It's something I assume you already know about. But something that maybe is not so familiar is the style of typing used in the Haskell programming language. So you might notice that I didn't write any type definitions anywhere. There are no types appearing in my code. Now you shouldn't conclude from that types are somehow not important in Haskell. They're extremely important. And Haskell is a strongly typed language. That is to say, you can't run any programs if the types don't fit together right. So this may seem a bit strange because we've not mentioned types at all, and yet I'm claiming that Haskell is strongly typed. So I'm claiming that Haskell is strongly typed like, say, Java, and yet I haven't written any types, as if I'm writing code in, let's say, Python. Well, the thing about Haskell is that it uses a mechanism called type inference. It infers for itself what types should be there. And it then checks, if you give it type information, whether the types that it's inferred are consistent with the types that are provided. Now, there are many reasons why we might want to provide types. An example here is the power function. The power function is a function which we've defined intending to work not on arbitrary numbers. So this is not something that we should be using on double precision floating point numbers, so-called doubles. We intend this to be used only on integers. So we could define that in a type signature, and the type signature will tell us that we want to use this for an integer first argument, an integer second argument, and thereby yielding an integer result. So this is a type declaration that has to be consistent with the type that Haskell will infer for this function. In fact, Haskell will infer a slightly more general type, but we don't want to use this function, for example, when k is a double, because it will go wrong. As you can probably imagine, if we're trying to do n to the power of 1.5, then we will get an error. Okay, any questions? Okay, having done that, having constrained the type of power here suitably, we could also now think about testing this guy. So how might we test it? Well, what's a suitable property of of this power function? Well, it should be consistent with the built-in power function. So if I have an n and a k, then what I get by computing power n to the power k should be the same as n to the power k using the built-in power function. And the types here will work out because I've constrained here power to only work with integers. So is that a good test? What do we think? Well, let's try it. Let's reload that. Let's do a quick check. Oh, quick check on prop power. Failed exception, power negative exponent. So this will work perfectly fine with the negative k, but this one won't. So this is not a good test of a property. This is not a property that holds for our power. Remember, we said that we want power to operate on non-negative k, so natural numbers. How could we build a test which will only use non-negative k here? Yeah, well, maybe. Use the abs function. So we could try and use guards, but guards really will tell us what we can do when k is positive. But quick check will still generate negative numbers that will have to be tested somehow. One way would be to say return true whenever it's negative. But a smarter way is to say, okay, let quick check generate any numbers it wants, any integer it wants for k, but we'll just use the abs of k. So we just use the absolute value of k for our exponent. Actually, this is something that is not a very nice style. It's repeated sub-expressions, but that goes really for any language here. So a natural thing would be to make a local definition. I showed you a where definition earlier. Let me show you another version. It's the let definition. So let k prime equal abs k. So let me give that a name in, and then this thing here, and I'll use k prime here. That's a slightly... Okay. Let me just try that again. And indeed, it passed at least 100 tests.
Question.
Yeah.
Can we use the let k prime? Did exist another way to do it with pattern matching?
Yeah, good question. So the pattern matching would mean pattern matching on positive k. There is a way of pattern matching on a positive k, but it's something which is sort of not really used in Haskell anymore. It's in one of the earlier definitions of Haskell. You could do pattern matching on something like that. which would insist that you match on something which was positive. Useful for defining this kind of recursion. You define what it does on n plus 1 in terms of what it does on n. You don't really see it used very much, and I think it's something that was considered a bit of a mess in the language design, a bit of a wart in the language design. It's not consistent with any of the other kinds of pattern matching, so it's generally not used very much anymore. So technically, yes, there is a way of doing it, but we're not going to use that. Yeah.
So then you need to use n minus 1 in your expressions.
That's right, but then we're not constraining k to be positive, as we would if we did with a +1 pattern. Okay, so we've seen a little bit about types. We can actually put types in other places in our code, and this serves to document our intentions. So this would be a double, for example. So it's optional whether we do this everywhere. As I say, Haskell will infer types, and the types that we write need to be consistent with what Haskell infers. And what I mean by consistent, Haskell may actually infer a more general type, something that actually works in more cases than what is done here. If you want to actually see types printed by Haskell, we can ask about the type of expressions. What's the type of true? It's a bool. But we can actually turn on, see if I can remember the syntax. So if I turn on types, then if I write true, now it will return not only the value, but what type it had. So it is just a shorthand for the last thing that was computed in the interpreter here. So this can be useful if you're not sure what types certain things have. You can explore them with these operations. And in particular, so we don't get any magic coercions between types as you might do in some other languages. So for example, if I try and add 1 and true, it won't actually run it. It will just say there's something wrong with it. Now the type error message is not, at this stage for you, is not very informative. So basically it's saying, woof, there's something wrong. It's a little bit hard to decipher at the moment because we need to know a little bit more Haskell before we can make sense of it. But it's basically sort of saying that in some worlds it would be possible to add 1 and true if true could be considered to be a kind of number, or if 1 could be considered to be a kind of Boolean. But that's not being the case, then this doesn't make any sense. Okay, any questions? Yeah.
This type of inference, does it often lead to bugs which are difficult to find because it's inferred some type which...
No, so the whole business of static typing leads to you finding a lot of bugs much earlier than you would. There's a lot of bugs that are caught before you run the program, because you can't run programs unless Haskell gives you a clean bill of health with regard to types. If there's any type error anywhere in your code, Haskell will say, I'm not running it. I'm just not going to run it. You get the types right, then I'll consider running it. But until then, it's an error.
Kinds of classes of numbers, for example. Like the power function you find, it seems perfectly right and would work in most cases. But then if one day a double gets passed into it, you get some error.
Yeah, but the error gets caught early because it gets caught at the time you write the code, not the time you run the code. So if you have something deep down inside which doesn't get used very often and doesn't trigger any errors in runtime, it doesn't matter, you'll catch that error already at compile time. So catching errors early is usually very cost efficient. Okay, let's move on to talk about a few other things. So there's a couple of other things I want to talk about today. One is not terribly interesting. It's called tuples, groups of things. Another is also groups of things, but groups of things of a slightly different kind, and that's lists. So two kinds of ways of grouping things together, tuples and lists. Tuples are used when the size of the collection you're grouping together is fixed. For example, 2 things, 3 things, 4 things. You fix the size, but the elements in the collection can all be of different types. Okay, so fixed size collection of things where the elements may be of different types. So I can collect an integer and a Boolean value, for example, and put them together in a tuple, a pair. Lists, on the other hand, are for collections of things where the size can vary. Could be no elements, could be lots of elements, could be infinitely many elements. But all the elements in a list have to have the same type. Okay, so either different types but a fixed number of elements, that's tuples, or all the same type but as many or as few as you like, that's lists. So tuples are, as I say, are slightly less interesting, but they're nevertheless sometimes useful. Here's an example. A function which takes a double as an argument and gives me a pair, that's the smallest tuple there is in this language, consisting of a Boolean and a double. So let's give an example of such an example. Example takes some number n and produces the value n is greater than, let's say n is less than 0, together with abs n. So this is a function which takes a number and produces a pair of things. The first thing is a Boolean value, it's true or false, and it will be computed by working out whether n is negative or not. If n is negative, you get the answer true, otherwise you get false. And you will pair that together with the absolute value of n. Okay? Okay, so that's an example of a tuple. Let me just compute that example on a, example on minus 42. Then you get the value true and 42. Any questions about that? Not very interesting example. So the size, so this is, you notice that the notation for building a tuple and the notation for the type of a tuple are very similar. Both use the brackets and commas. But remember, this of course is something in the world of types, and this is in the world of expressions. And these are separate worlds in Haskell. All right, enough about tuples. We can collect things together.
How do I extract a value from a tuple?
Very good. So the standard Haskell way of extracting something from a tuple would be to use pattern matching. So if I want to take the second element of a tuple, I would use pattern matching. So if my argument looks like this, then there's the second part. So that's how I can pull something out of a tuple. Now there are functions which will do this for you that are predefined, but they're really just defined in that way. They're actually called, if I take the previous expression and I apply the function first to that, then I get the first component of that. But first would be defined, and there's also similarly second, SND, which would take the second component of a tuple, but they're defined just like this in the prelude. They're just standard functions defined using pattern matching. So there's no primitive operation for grabbing pieces out of a tuple other than using a definition with pattern matching. Okay, any other questions about tuples before we move? Tuples are not very interesting. Useful, but not very interesting. Lists, on the other hand, are a lot more fun. So I've got spam there. Let's define some lists. So remember, lists are collections of things all of the same type. Here's something called snacks. What is the type of snacks? Well, it's actually a string. And here's my dinner, and it's a list, and we can build lists using this square bracket notation. There's a list of numbers, which it will assume are integers by default. So square brackets, elements between them separated by commas, that's the way of writing down a list value. But the primitive operations, the basic building blocks for building lists, are actually not the square brackets. This is really just a syntactic sugar. This is just a shorthand. There are two key operations for building lists. One is that guy, the empty list. That is to say, a left and right bracket together. That is a list. What type does it have? It's a list of anything you like, right? It's empty. So it can pretend to be anything you like. It can be a list of elephants. It can be a list of booleans, whatever you want. That's what it can be. That's one building block. The other building block is a small operator. It's the colon operator. It's an operator which takes an element, like number 1, and puts it on the front of a list. For example, the empty list. So what happens when you put 1 on the front of the empty list? Well, you get a non-empty list. What does that non-empty list look like? Well, when you print it, it looks like that. So this operation is pronounced cons, and it's for constructing a list. The terminology comes from the 50s in the programming language Lisp, which is built around the concept of building simple lists. Okay, so the type of cons is it takes an element on the left and a list of those elements on the right, and it gives you back a bigger list. So I can put, for example, 2 on the front of the list, 3 and 4, and I get the list 2, 3, 4. So they're the true building blocks of the list. Yes, question at the back.
Possible to do the other way around, so you put 2 on the end of the list?
We can certainly put a 2 on the end of a list, but we can't do it with a primitive operation, with a very basic operation. So lists are accessed from the front. All our basic manipulations on lists will be at the front of the list, so they're not doubly ended lists. So it's a good question. So lists are all the basic operations at the front. That means operations that operate at the far end of the list are non-basic. They will involve walking down the list to find the end. Okay, so here we have dinner. So if I actually compute dinner, of course it will replace the constants in here that I've defined with the real thing, namely, oops, what did I do there? And replace those with the actual strings. And actually, since I've got types turned on, I have to then tell you about something that's a bit odd looking here. You might have been expecting a list of strings, and what it said is got a list of lists of characters. So what it's actually revealing here is that string is actually just a shorthand for a list of characters. So the way that we write a string is just a syntactic shorthand for a list containing individual characters. Okay, any questions about that?
Unicode.
Yes, you can. It supports full Unicode if you're interested in characters, yes. I don't know much more beyond that. I don't know how to type them on my keyboard. But. Okay. What I want to tell you about is then functions operate over such lists. In order to be able to do anything with interesting with lists, we need to be able to do something with them. So let's take this example here. Let's suppose we want to have a summary of some list like this. So let me summarize my dinner by saying that if I have nothing for dinner, then that's what I summarize. So summary is going to be a function which takes a list of strings, a list of strings, and gives me back a string, and I'm going to define it by pattern matching. So what can I use in patterns? I can use any of my basic building blocks. I can use the empty list, that's one of my basic building blocks, and I can use the cons operation, that's this guy here, that's another one of my basic building blocks. And I can also use this notation with square brackets, that's just a shorthand for nils and conses all used together. Okay? So they're the things that I can use when I define something by cases. So here's a function that summarizes a dinner list. In the case when it has nothing, just says nothing. If it has just one element, I can pattern match on a list with one element like that. So this only matches a list containing exactly one thing. So I'm going to have just, and I'm going to use this list append function to join this string with this one here. So I can actually compile this incomplete definition, of course. So if I want to, if I have a summary of snacks, it would be, say, just spam, and a summary of nothing would just say nothing. Okay, let's make it a bit more interesting. I can keep going with a few more. Let's, for example, suppose there are two things on my menu, X and Y. Then I might summarize like that by saying X. Oops. X then Y. All right, now this could get quite tedious, right? I could go on and on and on. So I need some way of finishing here. I could define it for 2 elements, 3 elements, so on. What we typically would do here is give a recursive case or just give some general case. So I'm not going to do recursion just yet. Let me just give you a more general case. What does a more general case look like? All the other cases will consist of some first element followed by the rest of the list. So this will be the first item on the list, and this will be the rest of the list. Okay? So I might summarize this by saying let me just break this over several lines because I can. Okay, now suppose I want to grab the last element of this list here. Now I know this list is not empty. Why do I know that that's not empty? Indeed, it would match this case up here if it was so that we. And I know that it actually there is some other stuff before the last element. Otherwise, I would have matched this case here. So I know that there's actually at least 2 elements here. If I want to get the last element, I don't have a primitive operation for that. That doesn't mean I can't do it. In fact, there is an operation. It's already defined in the prelude. We'll have a look at how to define it in a minute. That would be the last operation. I can take the last element of the list. Let me just compile that. Oops. Okay. Now, let me summarize my dinner now. The summary of my dinner will be spam, then some other stuff, and then finally pudding. I could do with an extra space there, can't I? Okay. All right, so that's all worked fine and dandy. Now this is maybe not such a typical kind of definition. It has complex pattern matching but no recursion. Well, actually, there would be some kind of recursion defining last. So I mean, let's look at about functions over lists defined using recursion. I don't want to start with last. Let me start with something a bit simpler.
Question.
Yeah.
Do I have to use brackets?
Yes, I have to use the brackets here in the definition. Because otherwise it will think that I am applying summary to x, just x, and then applying the whole result to as the left argument to cons. So to summarize just quickly, there are operators here that are invisible. That space between the function and the argument is an operator. It's the function application operator. It's invisible, but it's there. The function application operator binds more tightly than any other operator. In particular, it binds more tightly than this operator. That's why we need the brackets. Okay, let's give a really simple example, simplest example of a function over lists, the length of a list. I'm going to call it len. It's going to take a list of things and tell me how long the list is. Okay, so typical case then is that we're going to define this by pattern matching. And here's the two patterns of interest. What happens when the list is empty, and what happens when the list is not empty? When the list is empty, how long is the list? 0 elements long. When the list is not empty, how long is it? It depends. Right? Yeah, it depends on how long that guy is. So it depends on the length of the rest of the list, but whatever the length of the rest of the list is, the length of this list will be 1 more than that. It'll be 1 plus that. You notice I didn't put any brackets around here. That's because, as I said just now, this operator here binds more tightly than any other operator, in particular the plus operator. Okay. Let's ask what the type of the length function is. Let me just reload that buffer and ask what the type of the length function is. Any idea what the type might be? It's a function, so it'll have an arrow in the type. Some list to an integer. Well, actually not quite. It's more general than that, but that's the rough shape. So look at this part for the moment. We haven't covered this stuff yet. It says it takes a list of any t. T here is completely unconstrained. So this is generic type. This is a polymorphic type. A list of anything you like, and it will give you back an A. What kind of A? Well, any A you like, as long as that A is a number. There's more than one kind of number. We've seen doubles. We've seen integer. There are other predefined doubles as well. Other predefined numbers as well. There are int, which are the short integers, ones with a bounded size. They'll be your standard ones. There are floats, which are half the precision of a double. So there's 4 types of number. So the answer you get from a length can be any one of those, depending on what you need it to be. So if you need it to be a float, it will give you a float. Okay, so this is basically saying if A has the right signature to be considered to be a number, then this function will give you one of those. But in particular, if I define it to be something which takes a list of anything you like and gives you an int, for example, a short integer, then that will compile. No problems with that. And of course, now I've compiled it, and I ask what the type of length is, it will be the type that I just said it was. So now I can't use it in quite as many ways, but you see there's a relationship between the type that Haskell infers is the most general thing that it can possibly think of, and sometimes the type that you mean is actually something a little bit more specialized. Okay, let me have a look at the last function that I used up here from the prelude. How would we define this function? Well, we might start by writing our little template. So what should we put in here and in here? What is the last element of the empty list? There is no last element. We've gone wrong. That's an error case. So that means that this was not the base case. This isn't the most simple case. This is an error case. It's not the same as a base case. We still need a base case. The base case is when we have just one element in the list. When we have one element in the list, the last element in that list is easy. That's just that element. What's the last element of a list which isn't the empty list and isn't a single element list? Indeed, it's the last element of the second list. So there's a definition of last. So I can take the last of a big list, the numbers from 1 to 100, just type them out for you. Actually, there's a shorthand for that, the dot dot notation, which can be used in a variety of different ways for a variety of different types that can be enumerated, and the integers are one such type. I can take the last element of the elements from 1 to 100, which is that list, and it gives me 100. Sorry, I was going to test my version of last. Unfortunately, that gives the same answer. Any questions?
Now, when we have a type constraint on the length, our type signature, we can't call it with double, for example.
No, we're only calling it with a list, so we can't use it. We can't use the answer as if it's a double. So if I do len of 1 to 100, the length of that list should be about 100, right? And I try and so what operation would force that to be a double? That would be if I wanted to add 1.1 to that. So I get an error. Okay, but what if I do the same thing with the built-in one, which will have the more general type? I think. No, it doesn't actually. Oh, actually, no. Length gives you an int. Okay, that's interesting.
If we remove
Yeah, we remove that. Let me try that now. Good question. Let's. Yeah. Oh, that was the prelude one. Yeah, sorry, stupid me. Ah, I'm having typing disorder. Then you see I get what I expect. So how does that work? Now, I'll just explain why that works. Why does Haskell give you such a general type? The reason is because the literals 0 and 1 are overloaded. They can have more than one. They can be considered to be of more than one type. So if I say I want it to be a double, then it can be treated as a double. So that's the reason why these types are so general, is because the integer literals are overloaded. Okay, in the last 5 minutes then, what I'd like to do is to just give you one more example of ways of building lists that doesn't actually involve direct recursion, but is actually quite a powerful operation. And that is something called a list comprehension. So a list comprehension is something which is taken straight out of sort of set theory notation, ways of describing sets of things, and applied to lists. It's an idea that first came into programming languages with some early prototype functional programming languages, less well known than languages like Haskell. It's an idea that has been taken over now and appears in a number of other programming languages since Haskell made it popular. Languages like Python also have these kind of constructs. So a list comprehension is a way of describing a list in terms of its components. So here I'm describing a list of all the things 2 times x, where x is taken from the list of things from 1 to 100, all right, let's say 1 to 20, and where x is odd. Okay, so I'm using a predefined function odd. So what do you think this might compute?
It will take for odd number from 1 to 20 and multiply it by 2.
Yeah. So the components of this definition are the generator. They can be more than one. They generate the things that you're using to generate the elements of the list. So we're taking all the possible x's from the range 1 to 20. This value here could be any function computing a list of values. It doesn't have to be one that looks like this. This here is a Boolean valued expression, something of type bool, which filters the things that we're interested in. This could be any Boolean expression. And this could be any expression which will be the type of the result that we're computing. And so here you see we get 2, 6, 10, 14, 18, and so on. We're taking all the odd elements of the list from 1 to 20 and doubling them. Okay? So this is called a list comprehension. Now, we can't define a function like last using a list comprehension, but we could define a function like len, the length function, with the help of some other functions. We could have defined the length function of some list x's to be adding up all the ones you get by taking elements x from the list x's. Stupid looking definition. The sum function is just adding up all the elements in a list. So if we were to do the list comprehension a bunch of ones by drawing x from 1 to 20, then we get a sequence of 20 ones, which we could add up. Okay, not a very smart way of computing the length function. Let's take another example. If we wanted to compute all the doubles of the elements in a list, we could double all the elements in the list by doing basically what we did down here. Then we produce a list of which doubles all the elements in its input lists. So there's fun things you can do. You can do a lot of these are very expressive. You can do a lot of things just with this very simple operation. We'll talk a lot more about lists next week. So we're not going to do much more about lists today. Any questions? Okay, so we haven't really covered a hell of a lot of ground, but you've got a first taste. Your taste here is enough for you to answer the questions in your very first hand-in part. That's the first lab. The deadline is on Wednesday, so it's time to install Haskell. You'll find instructions on the web how to do that and start playing with that. You'll find that the lab is not intended to be very difficult, really basically getting you up and running, installing Haskell, defining a couple of very simple definitions, doing a little bit of testing, the sort of thing we've seen today.